Hello friends, in continuation with the previous lecture, now we are going to talk about the next topic, that is nothing but the filters. Right? So filters, as we understand the meaning, is nothing but the filter out the things which are not required for us. Right? So here the filters which we are going to see is nothing but the frequency filters. Means that it does allow the certain frequency to pass, or else it can just stop the certain frequency to get transmitted over the distance. This is the something like circuitry which can allow or just stop the certain frequency of the given circuitries. Okay, so now here it is always desirable to amplify a certain signals, and that occurs at a given frequencies. Means certain frequency has to be transmitted. Okay, certain frequency only we are just talking about, not the all the frequencies are required. Whereas the sometimes we can have the range of the frequency, just like the certain frequency, if you consider just like the transmission of the our radio signals which were available in our cities, right? Or the range of the frequency is something like the radio frequency range is from the 88 megahertz to 108 megahertz. So that frequency is available for the radio waves. Okay, so the range of the frequency has to be transmitted. While now this is not only the problem with the transmitting the certain frequencies, also we need to suppress the signals other than the allowed frequencies. Otherwise there will be the noise, and the signal will get contaminated, and we may not be able to get the desired signal to be transmitted at the particular places. Okay. So the active filters are very useful and can be found by using the operational amplifiers. Right. The active filters have the passive elements like resistors, capacitors in conjunction with the active elements such as the operational amplifiers. Means we these active filters have the both the kind of the elements are used for the fabrication of the circuitries, passive element as well as the active elements. Now they uses the non-inductors so possible to integrate them. Also it can be used at very low frequencies where it is very impossible or very impractical sometimes to use the inductor circuitries. Inductor circuitry is something like the some coils are used for the generation of the frequency. So in such a cases we may not be able to use the inductors. So there we can use such a kind of the circuit. Now let's see the low pass filter. Means its name itself indicates that it allows the certain frequencies to pass. Means the low frequencies pass, and the higher frequencies has been rejected or the stop to pass, or the stop to transmitted over the that certain devices. Okay, the circuit diagram corresponding to it is shown over here. Something like, okay, we can see over here that is the circuit diagram for this is shown over here. How it is represented? It is something like operational amplifier having the gain is given by 10, and here the input at the input stage there is a resistance, and in the feedback we have connected the capacitors, right? So now do remember that for the low pass filters, the circuitry, the capacitor is in the feedback, and at the input stage there is a resistance. So at the low frequencies what happens that the capacitive reactance, which is given by xc is equal to 1 over omega c, becomes a very large, and the circuit acts as a inverting amplifier with the gain given by minus R2 by R1, right? So why minus R2 by R1 as a gain? Because the input is provided to the inverting terminal of the operational amplifier. So we know that the gain of the amplifier, inverting amplifier, is the minus R2 by R1. So here then the capacitive reactance is given by 1 over omega c. So c is a fixed, but as the frequency gets increased, obviously this reactance becomes a very uh, uh, low for the larger frequencies, and the lower frequencies this becomes very large, and so it can be acting as the inverting amplifier, and the gain is provided over here is 10. For the certain this gain can be varied when the frequency of the input voltage is increased. Okay, frequency we are increasing, so obviously reactance gets decreased, so the capacitive reactance of the capacitor gets decreased, thereby decreasing the voltage gain, so it decreases the voltage gain. Now at the infinite frequencies, the obviously gain approaches to the zero ideally, because then the capacitor appears to be shorted. As the frequency gets very high, then obviously this becomes a shorted. Whether it doesn't matter that whether the capacitor is present or not, but it is just for the higher frequency we can, it will be acting as just like a feedback gain. So output will be just multiplied with 10 times the input. So but gain will go on decreasing, and we will get the zero output. The active low pass filter response curve is shown in the figure below. So if what we can say, at the lower frequencies we can have the capacity reactance is very high in the feedback, so that we can get the high gain of this, and as a certain frequency reaches to the cutoff. Okay, so this cutoff frequency is called as the higher cutoff frequency, because we are dealing with the low pass, because low frequencies are allowed and high frequencies are stopped. So beyond this point, 1 by root 2 times the maximum amplitude, because we are dealing with RMS value, so we can have the 1 by root 2 times the maximum gain or the amplitude times. So this frequency, above this frequency is cut off, not allowed to pass through the filter. That's why we call it as low pass filter. Low frequencies are allowed to pass. Input impedance is Z1 is equal to R1, and the output impedance, which is given by 1 by Z1, 1 by Z1 is equal to 1 by R2 plus 1 over XC, 1 over XC. Output impedance we are just talking about, because both are in the parallel one. If we look back to the circuitry, that the here 1 over R2 is in parallel with the 1 over XC. So they are feedback resistances are parallel. So this will give us the 1 over R2 plus j omega C. So the ratio of the impedances is given as 1 Z2 by Z1 is equal to R2 by R1 plus into the 1 over 1 plus j omega C R2, where j is here the complex number is equal to 1 root minus 1, root minus 1. The absolute value of the ratio of the impedance is given by R2 by R1 into 1 over root of 1 plus omega C R2 bracket square. So this actually represents the absolute value of the ratio of the impedances. It shows that the gain is maximum at the lower frequencies and decreases with the increase in its frequency. If you can see over here that Z2 by Z1 is the gain. So as the frequency goes on increasing, obviously this ratio becomes a smaller and smaller one. So obviously this indicates that the slope goes on decreasing after the certain frequencies are just increased beyond the cutoff point. Now, apart from this, now the next amplifier is the high pass amplifier. As we can see back to the low pass filter, the in the circuit diagram, what we used to have, this capacitance is in the feedback, but now in case of the high pass filter, the capacitance is at the input stage, so this is the only the difference between the low pass and the high pass one. If we change the position of the capacitance, obviously we can just switch between the low pass and the high pass filters. So obviously gain remains same, that is R2 by R1 with the negative sign for the inverting amplifier, and the cutoff frequency is given by 1 over 2 pi R1 C. The cutoff frequency also here is the same, well, that is the 1 over omega C of the capacity reactance was there. Now the input impedance of the circuitry is given by here, that is Z1 is equal to R1 plus J 1 over J omega C, because this impedance of the capacitance plus this resistance, they are in the series. So what we can have, the R1 total impedance is R1 plus j omega c. Impedance is related to the resistance in the DC circuits. When we deal with the AC circuits, then the total resistance will be replaced with the impedance plus its resistance. Okay. Reactance plus the resistance gives us the impedance of this circuit. And if we just rearrange the terms in this, we'll get the 1 plus j omega cr1 upon j omega c. J is as usual our complex number. The output impedance is given by Z2 is equal to R2, because there is nothing, no capacitance is there. So output impedance is whatever there is, the feedback resistance will be. So the amplifier gain is again the minus R2 by R1. The gain of the amplifier is given by now R2 by the R1. So what here we can just replace the gain of this amplifier as Z2 by Z1, because we are dealing with the impedances AC sequence. So Z2 by Z1, just try to substitute the values over there, and what we can say, the j omega c R2 upon 1 plus omega c R1. The output response of the high pass filter is shown over here. That is at the this is the cutoff, lower cutoff frequency we call it as, because that the low frequencies are not allowed, and after this cutoff frequency all frequencies are allowed. So now this as usual, the amplitude is on the y-axis, the vertical axis, and the frequency on the horizontal axis. Okay. Cutoff frequency is given here. uh, Now the absolute value of the gain is given by mod of Z2 by Z1 is equal to omega c R2 upon root of 1 plus omega c R1 square. So just normalize it by just using the complex number with its complex conjugate. Now at the low frequencies, the capacitance appears to be open, and the output of an amplifier is very small. But at what happens at the high frequencies, that the capacitive reactance is very low, and it acts like a short circuit, and becomes an inverting one. So this is all about the uh, filters. Okay, high pass filters. Thank you.